Yes, we're already at lecture 15. Last lecture was really exam. How did it go? Hard? Awesome. That's good. Well, we'll go over the distribution. But to remind you, today you have a homework due. And there will be homework 5 due April 2nd. We have a bunch of concepts that we're going to cover today and during the next week. Lab assignments, hopefully you don't forget because of the spring break. Your control flow and branch prediction lab is due this Friday. And you remember that you can get extra credit by optimizing your design. And I will announce who got extra credit today for lab 3. And lab assignment 5, which will hopefully be even more fun, will be out Wednesday, and it's due April 6th. And in that lab, you will essentially go to higher level simulation. You will start with a C-level pipeline implementation of the MIPS processor, not the Verilog that you did. This will be given to you, and you'll add caches as well as branch prediction to that implementation, and you'll have a lot of opportunity to explore at the higher level. And you will see, hopefully you'll recognize how fast it is to explore at that level versus at the Verilog gate level. Okay, but first you should finish this. Okay, feedback sheet, you can still turn this in. I'm going to impose the deadline, which is March 25th, which is a very lax deadline, if you will, which is after your lab. So I would appreciate it if you turn this in. I didn't receive enough feedback sheets, I think. Okay, midterm 1 grades. You guys might be looking for this. All of these grades are, by the way, posted. Lab 3 grades, midterm grades, as well as your mid-semester grades. They're all posted on Blackboard. So let's take a look at midterm 1. What's the hard test? Yeah. It was the hardest you've ever taken? It wasn't that bad, right? Okay, well, there's a distribution. It was out of 335, and you had a 40-point bonus question. The average is around 175, and the median is very close to the average. The maximum is, I was expecting someone to get 375, but that didn't happen. Hopefully in the next midterm, or the final. So someone was relatively close, though, 281. So if you didn't do, if you're around here, then this is the dangerous zone, right? This is not very, you should be studying harder. And you can certainly come to us, talk with us. And this is the first midterm. It's 15% of your grade. There will be another one, and there will be the final. Yes?
Is there going to be a curve looking at the grade?
Yes. Yes, there will be a curve. And all of your mid-semester grades are also curved, including every assignment that you did so far. Okay? Okay. So midterm solutions, these are posted online. This is perhaps even more important than your grade because you can always improve at this point. Check and make sure you understand everything. And this is the first midterm. The questions will be similar in the next midterm, although it will be on different concepts. And these questions, the same concepts that we've encountered, will be there in the final, which is 30% of your grade. And TAs will cover the midterm solutions, will dedicate the lab sessions, the discussion sessions, this week and early next week to midterm solutions. So that's a great way to actually go and, even if you did well on the midterm, refresh the topics we've covered. So you can go to discussion sessions, and discussion sessions will be dedicated, except for perhaps the Friday one, where people will likely check off their labs for the midterms. Okay? So this is for you to look at, just a little bit of analysis on the questions, if you remember the questions. A lot of people didn't get the mystery instruction. You remember the mystery instruction question? That's a reverse engineering question. So that mystery instruction was essentially the find first instruction, which is implemented in VAX. Or, I guess, bit reverse scan? Was it? Yeah, it's also in x86 apparently. I didn't know that before Chris figured that out. It was essentially finding the most significant set bit the index of the most significant set bit in a 16-bit register, assuming the register is not 0. Okay? So some people got it right, of course, but that was one of the harder questions, apparently. The other hard question, which is actually an easy question, I think many people did not attempt this question, the bonus question, was this, where you would actually write MIPS code for saving registers and figuring out the trade-offs of when you actually are better off with the sysg instruction and when you're better off saving the individual registers themselves. And if you remember this question, that was again another reverse engineering question, if you will. These questions are good for testing understanding, so it's good for you to take a look at it and see how you fared on that. That was the rename logic of a superscalar processor, a 3-byte superscalar processor. Okay, so homework 3 grades, I'm not going to cover that much homework. You can see where you are here. Lab 3 grades. So several of you actually got points more than maximum possible because you got a lot of extra credit, because you turned in early or did well optimize your design. If you're around here again, if you're struggling through the labs, you should talk with us. Come to office hours, come to lab sessions, talk with the TAs, and figure out what you did wrong. Okay? And these are the results for the Lab 3 competition. Basically, 8 of you had fully correct designs, I think out of 49 of you who submitted. And 4 students shared the fastest design. And I gave 10% extra credit for all of you, all of the 4. And if you look at the top 4, I don't know why this is not coming out. This is supposed to be red. It is red here. Let's see. If we do this magic, will it be red now? Maybe this projector is not displaying red. Okay. Okay. Rui, Jason, Taylor, and Jonathan, they were all within 6% of each other in terms of relative execution time, and there was a big gap between the 4th and 5th, if you see the relative execution time here. And if you look at the fastest design, this is on a, I guess, large program, right, that you tested.
Set of 5 random programs.
What program?
Set of the 5 random programs.
Oh, okay, set of the 5 random programs. If you look at the best design, it's not the best design with the, well, I guess it looks like the best design with the best cycle time in this case. But it's not the best design with the number of cycles. So the number of cycles greater than Tyler's design, right? But, and top 3 will soon earn a book each. And that soon was 15 seconds from now, but I forgot to bring the books. So you'll earn the books next time. Okay? So if you actually optimize your designs, you'll get rewarded, and it's a lot of fun. Okay, well, I guess the 15 seconds will not work right now. Next semester, not next semester, next week, or next Monday, on Wednesday. Okay, so readings for next time. We're going to start memory hierarchy soon. We've covered a lot of computation and the pipeline so far. You should read the cache chapters from Patterson and Hennessy. These are chapters 5.1 through 5.3. And memory cache chapters from Hammaker. This is a recommended book, 8.1 through 8.7. And the first cache paper that was published in 1965. That's only a 3-page, or maybe a 2-page paper. It's relatively short. That just gives a basic idea of caching. Do we have a problem with the... Can you guys see the colors, or is it me that's becoming colorblind? This is supposed to be red or blue, one of those. Red. It's not red? Okay, good. You know, I could become colorblind too. It happens. There's temporary color blindness too. That happens, right? Okay. I guess let's see. Okay, last lecture we covered the reorder buffer, the future file, and in-order pipeline with precise exceptions, how to put those two together. And we covered out-of-order execution. And I understand that you did that in the review session as well. So, and you had a question in the exam on out-of-order execution. I guess that's not going to work. All right, we'll have to do without color. And somehow, could you send an email to the appropriate people to get this fixed? Today, we'll wrap up out-of-order execution. I tend to go relatively fast. I'd like to give you an overview of some alternative approaches to concurrent processing. Out-of-order execution is one way of extracting concurrency out of a single instruction stream. Right? And it's really a restricted data flow machine. An out-of-order machine is a restricted data flow machine. So we will go back to the data flow that we discussed earlier. And we will talk about how that extracts parallelism at the ISA level. And then we will go into vector processing. I think that's an important concept that you should know in an undergraduate computer architecture course. Mainly, well, partly because of the rise of the GPUs. GPUs are essentially, graphics processing engines are essentially vector processing engines. So we will see how they work at some level. But let's continue with out-of-order execution a little bit. Remember, there were 4 things we did to enable out-of-order execution. Link the consumer of a value to the producer. This was register renaming by associating a tag to each data value. We buffered the instructions until they're ready. Right? We took them out of the way of independent instructions by using reservation stations after renaming. We kept track of the readiness of the source values of an instruction inside these reservation stations. And we did this by, when an instruction executes, it broadcasts its tag when it produces the value. And all instructions that are waiting for the tag that were already linked with the register renaming capture that value, as well as say that, oh, my value is ready now. And when all values of an instruction are ready, then the instruction is dispatched into the functional unit. Basically, instructions woken up and scheduled by this hardware scheduler. And that's the out-of-order execution in a one-slide summary, basically. And remember, we did this example in class, and I asked you to do some of these things on your own. These are relatively easy for you by now. I just want to cover what we did in class was without precise exceptions. Adding precise exceptions to out-of-order is relatively easy, right? It's the same idea. Use a reorder buffer at the end of the pipeline. And instead of writing the result directly to the register file, reorder the instructions before committing them to the architectural state. Which means that you need to have an architectural register file now, right? Remember, you have the register alias table at the front end of the machine, which contains values and tags and ready bits. Now, at the back end of the machine, we should have an architectural register file that's essentially the state of the registers that's visible to the software, right? Basically, it's essentially the register alias table. If you think about it, it's a future file, right? Because it's updated when an instruction completes execution. You update the value there, and architectural register file, the back end of the machine, it's updated when the instruction is oldest in the machine has completed execution. So this is the same as what we did for an in-order machine with multiple functional units that took different amounts of time. Make sense? So this is what the machine looks like. Basically, after renaming instructions, we put them into the reservation stations, and renaming happens in order. Within this, from the reservation stations, instructions can get scheduled out of order into the execution unit. So this part of the machine is out of order. And at the end of execution, the instruction values broadcasts its tag and value, and updates the register alias table here. And it writes its result into the reorder buffer. And when it becomes the oldest instruction, it updates the architectural register file. So architectural register file is updated at the end of the pipeline when the instruction becomes the oldest. That's how you maintain precise exceptions in out-of-order engine. And this is how almost all modern high-performance processors operate. If you look at, I don't know what Intel calls its latest processors now, but Nehalem, it's like this, basically. At a fundamental level, it's the same. OK, so summary, renaming. We did renaming to eliminate false dependencies and link instructions to each other. Tag broadcast enables value communication between instructions. Right? This is the part that's data flow, like, if you will. What you're doing is really you're sending the value, communicating value directly to the consuming instruction. You're communicating the data directly to the consuming instruction. And when the instruction has all of its sources ready, it's firing. Remember the data flow? And node fires when all its inputs, all its sources are ready. It's essentially the same concept that's done at the microarchitecture level. And essentially, an out-of-order engine dynamically builds a data flow graph of a piece of the program. Does that make sense? You guys know about data flow graphs? If not, we will cover them soon. And I'll have a question for you. So what piece does it build? Remember earlier when we talked about data flow, you program, and your program is essentially a data flow graph of the entire program. Here, out-of-order execution doesn't require that, right? It dynamically builds this data flow graph, if you will. And that data flow graph is really limited to what you have in the instruction window. Basically, the set of instructions that are currently in the machine that are decoded but not yet retired. Make sense? Because those are the instructions you linked to each other. Right? So we'll see how this happens. I guess, can you do it for the whole program? Well, that's what a data flow machine is, right? You could potentially do it in an out-of-order machine for the whole program also, but that will require, think about how to increase the size of the instruction window, the set of instructions that are currently in the machine. You need to increase the size of the reservation stations, right? And the reorder buffer, and the register file. Okay? How can we have a large instruction window efficiently? I will not answer this question, but we may get back to it later. Okay. So let me ask you this question. Why is out-of-order execution beneficial? Yes?
You don't have to wait on dependencies that normally occur in order executions. You're not stuck behind something that has a dependency on something forward when you don't have that same dependency.
That's right, yes. So you basically extract independence from the program and execute things in parallel. Let me ask you another question. What if all operations take single cycle? Is out-of-order execution useful? Yes? No? Maybe? So let me get back to that again. So what out-of-order execution brings you is the latency tolerance, right? It enables you to tolerate the latency of multi-cycle operations. If you have a long operation, now you can execute some other independent operation while that longer operation is happening. So if all operations take single cycle, it's not as beneficial, right? But you could have multiple different dependency chains, if you will, in your program. If you get to that dependency chain that's independent, and if you can fetch it earlier, even if your operations take single cycle, you can still get benefit from out-of-order execution, right? But then you'll have to somehow get to the dependency chain. So let's say your data flow graph looks like this. And each of them is a single cycle. A bunch of dependent adds. Well, I'll do this, I guess, for add. You can execute these single cycle operations in parallel with other single cycle operations. And these could be executed out of order, right? So in a sense, you can tolerate the latency of this entire big dependency chain by executing this independent dependency chain in parallel. Does that make sense? Of course, here you will need to have the ability to fetch more than one instruction also. But if you're fetching only one instruction, then out-of-order execution is not beneficial if each of your instructions take only one cycle. Right? Does that make sense? Okay. So I'd like you to get thinking from this direction. Basically, the main benefit of out-of-order execution is the latency tolerance benefit. You tolerate either the latency of a long latency instruction or the latency of a dependency chain that you need to execute by overlapping it with other independent things that happen to be in the program. Right. They don't have to be all adds, but it's all adds here. So what if an instruction takes 500 cycles? Let's say one of these instructions, this instruction, hopefully not an add, maybe a load. It takes 500 cycles. How large of an instruction window do you need to tolerate this latency? You need to be able to look ahead some number of instructions to find independent things, right? Well, usually if you don't want to stall your processor at all, let's say this instruction takes 500 cycles, and you're fetching 4 instructions per cycle times 500 cycles. Basically, you need an instruction window of 2,000 instructions. You need to have the ability to buffer that many instructions so that your machine is not stalled while this instruction is taking 500 cycles. Right? Yes?
Are these instruction streams all in the same thread?
Yes. This is assuming all of this is in the same thread. Right?
So it's not like hypothetically you have multiple, you have one core acting as multiple cores.
That's right. It's all in the same thread.
So isn't it like how likely are you to find, like, if you have 500 instructions, like looking at that much, usually how many instructions can you find that actually?
That's a good question, actually. It depends. It depends on the program. So if you're doing a linked list traversal, for example, everything could be every future thing could be dependent on the previous thing. But there is actually a lot of dependence in programs. So what you could be doing is, for example, loading a value into R1 and testing the value and then branching on it. And everything else that comes after it could be independent. There may not be any data dependence. So it turns out there is a lot of independence in the programs. It's hard to quantify. It really depends on the program. But one other example to motivate this is you could go to a next loop iteration that's independent. So you could have a for loop, for example, I less than x, I plus plus. And maybe you load some values and you have some dependence chain here, and nothing is independent of each other within the loop iteration. But when you go to the next iteration of the loop, you load something else and overwrite register 1, and that leads to a totally independent loop iteration. So you could overlap multiple loop iterations with out-of-order execution. So it really depends on your program. If your loop iterations are dependent on each other, then you don't have a lot of parallelism. So it gives you a lot of fine-grained parallelism, if you will. Even within the loop iteration, there may be some instructions that are independent of each other, and you can execute them in parallel. Okay. Okay. I think I will, just to finish this point, basically the latency tolerance scalability of Tomasulo's algorithm is really limited by this active instruction window size. It's determined by your reorder buffer and how many instructions you can buffer. Right? Beyond that, you cannot find independent instructions. And if you don't want to stall your machine ever because of a long latency operation, what you need to do is find your longest latency operation and multiply its latency with the fetch width and provide buffering for that many instructions. Obviously, this is a lot of instructions to buffer, right? So if you look at some existing processors, I think Pentium 4 had a 126 NP instruction window. And that was one of the larger machines. I think, what are the size of the current Intel machines? Is it 96 or?
Sandy Bridge is 160.
160, okay, there you go. Sandy Bridge is 160. And increasing the size of this window is actually difficult because it's very power hungry. Think about the reservation stations, right? When an instruction executes, you need to search the entire reservation station with the tag. It's a content associative memory. Right? So that limits the scalability of the out-of-order engine. Okay. So some food for thought for you. I will not go into detail all of these, but you should think about how to put together some of these concepts. Basically, how can you implement branch prediction in an out-of-order execution machine? What are the difficulties? It'd be good for you to think about it. Think about branch history register and pattern history table updates, for example. Now you're executing branches out of order. Is there an issue with that? So a lot of machines, what they do is they update these structures when the instruction actually retires. But is that the right thing to do? I mean, or is that the best performing thing to do? What if you have a very tight loop, and as I showed you here, out-of-order execution, if you have a 160 entry instruction window, and if your loop size is 10 instructions, you can have 16 of these iterations in your machine, right? So by the time you update your branch predictor, you already fetched 16 iterations into your machine. So think about how this affects things. These are real design decisions that processor designers make. When do I update the branch predictor in an out-of-order machine? How do you recover from branch misprediction in an out-of-order machine? Now you could have many branches in the machine, right? Let's say a later branch resolves because it's independent of previous branches. Do you recover the state right away? How do you recover the state right away? Do you have the precise state for each branch at every point? Think about that too. How can you combine superscalar execution with out-of-order execution? What I would like to emphasize here is these are different concepts. Unfortunately, superscalar execution is used to mean both sometimes used by some people to mean both superscalar and out-of-order, but these are different things. Right? Superscalar means fetching multiple instructions per cycle. Out-of-order means you can execute instructions out of order. You can design a machine that's not superscalar but out of order, right? Single wide fetch, but out of order. Or you could design a superscalar machine that's in order, right? That doesn't have reservation stations. In fact, Pentium, Intel Pentium was that way. Yes?
What could be the advantage of having a superscalar in order?
What could be the advantage?
Because you're fetching, let's say, 4 instructions, you still have to wait on each of them.
Not necessarily, unless they're all independent, right? If they're all independent, you're essentially executing 4 instructions per cycle.
But if you're not doing out-of-order instruction, out-of-order execution, you can still fetch 1 instruction each time and still get the same output, right?
No, so with a superscalar machine, you're fetching, decoding, executing, and committing 4 instructions per cycle, let's say, or n instructions per cycle. If all of them are independent, then you improve your throughput, 4 instructions or n instructions per cycle. You don't need out-of-order execution, right?
So it's like you have 4 different processors running.
That's right, yes. You have 4 pipelines that are running in parallel. Okay. So if you put these two concepts together, so if you have an in-order superscalar engine, you don't need to rename instructions, right? You just need to figure out the dependencies between instructions. And if you have a dependency, you just stall one of the instructions. But if you actually combine these two things, now you need to concurrently rename multiple instructions. So this increases your complexity. You need to concurrently broadcast tags. And of course, the next question will be, how do you combine superscalar, out-of-order execution and branch prediction together? Now we're building a machine that resembles today's microarchitectures. Okay, some more food for thought for you. I think I'll go into a little bit more detail on this because it's an important concept. How do you handle load and store execution in an out-of-order execution engine? Can anyone think of issues related to this? Remember, we're scheduling or starting to execute instructions when their sources are ready. An instruction fires, if you will, gets to the execution unit when it's ready. When is the load ready? When its address is computed, right? Or when its source register that's needed for its address computation is actually ready. So let's say you have a code like this. Add, multiply, store. Let's say these are dependent on each other. And then, let's say you have an add, and you have a load. And let's say this load is independent of the store. And you're doing out-of-order execution. Let's say this load becomes ready. This load is loading from register 0 to register 1. And the store is storing something in register 5 and multiplies writing into register 5, computing the address. Let's say add is also writing to register 5, computing the address. So you have dependencies here. Well, I guess store to a register 5 based offset location. Okay, so this load may be ready before the store's address is known. Right? Does that make sense? It could happen, right? You're executing things out of order. So how do you handle this in an out-of-order machine? This is one of the most complex parts of existing processors, actually. Well, a younger load can have its address ready before an older store's address is known. And this readiness is determined in the machine, right? You cannot do renaming, register renaming to figure this out because store's address is not available until it executes. That's the difference between memory and register dependencies. Fundamental difference is that you know the register dependencies by just looking at the code. But you don't know the memory dependencies by just looking at the code because memory addresses are based on register values. And register values become available when you execute. So you cannot determine this dependency until the store executes and its address is computed. Well, this is known as the memory disambiguation problem or the unknown address problem. If a later load is ready before you know the address of a previous store, what do? Well, there are several approaches you can do. Actually, you could. Why don't you tell me? What would you do? Yes?
Just like we do branch prediction, we could actually run the load and keep it in an alias table for the memory. And if the store address is not the same, then it should be fine. So if the store address is the same, you could just do some manipulation and transfer it over.
That's right, yeah. So you're suggesting basically, assume that this load will be independent and execute the load when its address is ready. Right. And later when the store executes, check whether this load executed correctly or not. Right. Whether the store's address actually overlaps with the load's address. And that's one approach. And that's a predictive approach, if you will. Always assume the load is not dependent on a previous unknown address store. Well, that's definitely not the conservative approach, right? The conservative approach is basically store the load until all previous stores have computed their addresses. Right? And then you can check whether the address matches. And get the data, forward the data from something that's called a store buffer. Yes?
Do you install the instruction in like the pipeline, or do you install it in memory controller?
So you stole it at the reservation stations, right? Remember, this load is waiting in the reservation stations, and it's already selected for execution, but there's another check that it needs to perform. Is there another store in the machine with an unknown address? And if the answer is yes, then this load cannot get scheduled to the cache, basically.
Can you like dispatch the instruction, but like have a cache just take a long time to get me to actually be the memory?
You could do that, but then you will still need to wait for the store, right? You somehow need to figure out you need to wait for the store.
Like just like where do you put that logic?
Yeah.
Like where would you put the logic though? Like would it be in the memory controller?
No, you don't send it to the memory controller. It's all in the core, processing core. Okay. It's because if you send it to the memory controller, how are you going to check whether the store matches?
Well, the memory controller checks, and if it detects that it matches, then it just doesn't return any data until the store is completed.
I think what you're thinking of is cache controller, right? Yes. Yeah, you could do it over there too, but that's another approach to the problem. So what modern processors do is you have this load store queue, if you will. When a load computes its address, it checks the structure. And you could put it at the memory controller, but it's usually put before the cache controller. When a load computes its address, it searches its address in this load store queue. And if there is a matching store that has completed, you get the data from that. Of course, this needs to be ordered, right? You have to get the data from the latest matching store, if you will. So it's a very complex logic. And if there is a store with an unknown address, then you decide what to do. You can stall the load. Okay. You could be aggressive, as you suggested. Assume load is independent of unknown address stores and schedule the load right away. Of course, now you need to provision for when you're wrong, right? You need to figure out when you're wrong and re-execute the load. Or you could be, I guess, intelligent in the middle. You could predict with a more sophisticated predictor if the load is dependent on any unknown address store, right? Or on a particular unknown address store. And this is what existing machines employ, in fact. They do prediction. Conservative is too conservative because it turns out most loads are actually independent of previous stores. Well, except for stack communication. If there's a store that's writing to the stack, and if there's a load reading from the stack. Those are the communications that usually tend to provide store load dependencies. Okay. Okay, so I think I told you this. Basically, how does the auto-ordered engine detect dependence of a load instruction on a previous store? You can wait until all previous stores are committed. This way, there's no need to check, if you will. You can just execute the load. But this is very conservative, right? Or you can keep a list of pending stores in a store buffer. This is what I showed you here. And check whether the load address matches a previous store address. Okay? And how do you actually treat the scheduling of a load instruction with respect to previous stores when you get the address? These are the three options that I listed earlier. Assume load is dependent on all previous stores. Assume load is independent of all previous stores. Or predict the dependence of a load on an outstanding store. Let's take a look at the trade-offs related to this. But if we assume that load is dependent on previous stores, I already told you that it's conservative because it delays independent loads unnecessarily. Right? Of course, there's an upside to everything. The upside is there's no need for recovery in this case, right? You don't need to figure out you're wrong, whether you've done the wrong thing. Because you're always doing the right thing here. You're always waiting for the worst case. Second option is you can assume the load is independent of all previous stores, even if you have an unknown address. In this case, the upside is, it's again relatively simple and can be common case. No delay for independent loads. An analogy suggests that this is more common than the first option. The downside is it requires recovery and re-execution of loads. Re-execution of load and dependence. The third option is being a little bit more intelligent, predicting the dependence of a load on an outstanding store. This turns out to be more accurate because load store dependencies persist over time. So you can think of why it could persist. Let's say you have, well, this was one of the questions in your exam, right? You had this, well, you did this before also. Basically, you have a function call. Before the function call, what you do is you do a bunch of stores, right? You save the registers on stack. And after you return from the function call, what happens? You do a bunch of loads. You load back the registers from where you saved them, right? So obviously these store load dependencies are very predictable, right? You have a matching load for the store for every register you saved with a store. So that's the reason why this predictor could work well. That's one of the reasons. And this could all be in your instruction window, right? Let's say this function is 10 instructions. And you have 5 stores here, 5 loads here. That's 20 instructions. Well, Chris told me that you have some 160 instructions in Sandy Bridge. So you could have many of these. Let's say you have a loop that does this. You could have 16 of these, if you will, in the machine at the same time. So you could actually predict. If you predict these, then you know exactly which store to wait for. Make sense? It's more accurate. Well, downside, it still requires recovery, re-execution on misprediction, and also it requires the ability to predict. which store the load is dependent on. So this is actually implemented in a lot of machines. Alpha 21264 has a very simple predictor. What it does is that initially, the first time you execute a load, if you see an unknown address store, you assume that the load will be independent. And it checks if that was the right thing to do. If the load actually turned out to be dependent when the store is executed, then what alpha does is it marks the load in the instruction cache with a bit, saying that do not do this again for this load. Do not assume that it's dependent. It's independent. So the next time that load is executed, it has this additional bit in the instruction cache that's not visible to the architecture. This is part of the microarchitecture, saying that don't assume that this load is independent of previous stores. So the load comes into the machine, checks this bit, and the bit says stop, stall basically, and the load gets stalled until all previous stores are finished, compute their addresses. And it turns out that improves performance significantly. And some of these papers describe that, describe even more sophisticated schemes. So it turns out predicting store load dependencies is important for performance. So if you look at this, this is a sample. This is one thing you can do if you have high-level simulation like what you will have in your lab, for example. You could add three things. You could have no speculation. In this case, no speculation means I think essentially assume that the load is dependent on all unknown address stores. You could have naive speculation, as they call it. Assume that load is independent of the previous stores. And this is the impact of perfect prediction, if you will. What if you perfectly predicted which store you were dependent on and only waited if that store had an unknown address? You could do this in high-level simulation, right? You could actually figure out this perfect mechanism and simulate it. And that's what Christos and Emmer did. They looked at the performance impact, IPC impact, of these three mechanisms. This is an unimplementable mechanism, right? You perfectly cheat in the simulator to figure out whether you should have waited or whether you shouldn't have waited, right? And you could do that. It's all in software. And they plot the IPC of different applications from the spec suite, if you will. I guess they don't have an average here. But if you look at this, no speculation is usually worse than naive speculation, confirming that it's better to actually speculate that this load is actually independent of the store. But there's a huge gap between perfect and naive speculation, which means that you're better off if you can somehow predict whether you should wait or go. And simple predictors, one of which they describe, which I will not go into in that paper, in that ISCA paper, can achieve most of the potential performance. And Alpha's 21264 predictor is very simple, and actually it achieves quite a bit of this, and they show that in the paper as well. Make sense? So you see that there is a significant performance difference. Well, I guess for this application, for example, IPC is 2, and this is an 8-wide machine, 8-wide superscalar machine. IPC is 2 with, if you take the conservative approach, IPC is about, what is that, 3.5, 3.3. If you take the aggressive approach, and IPC goes up to almost 6 if you actually are perfect in your prediction. Okay, so more food for thought. There are many other design choices in an out-of-order engine that we will not be able to cover. Otherwise, you may want to spend the rest of the semester on this. I go into a lot more depth in my 740 course, if you're interested, and if you're still here. We talk a lot about this. For example, one thing I'll leave you with is, should reservation stations that we discussed earlier be centralized across functional units, or should they be distributed? Right. The reservation stations we looked at were distributed across functional units. But some machines actually had centralized reservation stations. Pentium Pro, for example, it was implemented as a centralized, I think it was a 40-entry reservation station across all functional units. Some other machines like PowerPC 604, that was one of the first machines that had distributed reservation stations. For the adder, you have some reservation stations. For the multiplier, you have some reservation stations. But you cannot use, of course, the multiplier as a reservation station for the adder. Right? In a sense, you have some storage space. Do you dynamically partition it between different functional units, or do you statically partition it? So you can think of what are the trade-offs related to this. I'll give you some hints, I guess. If you have reservation stations that are centralized, then you're not dependent on your instruction mix, if you will, right? If all of your instructions are actually adds, you can accommodate them in the reservation stations. Whereas if you partitioned your reservation stations, and if you had only 4 reservation stations for your adder, well, what if you get 20 adds in your instruction window? You cannot accommodate them, right? And if you actually centralize your reservation station, what you lose is you cannot specialize your reservation station now for the units, right? Every entry in the reservation station needs to be general purpose to accommodate all possible functional units. But not all functional units need everything, right? Think about the branch functional unit, for example. You don't really need 2 sources as long as your branch instructions do not have 2 sources, right? Okay? So you can think of some of these things. And this is a required reading, so a required reading actually covers a lot of these things. But if you want to see how a relatively modern processor is designed, this is a very good paper that describes the design choices in the Alpha 21264 microprocessor. It talks about the branch predictor. Well, we talked about Alpha's branch predictor, the tournament predictor, right? Local, global, and a selector. But it also goes into a lot of other details about the out-of-order execution engine implementation. And this is a relatively nice read. I would definitely recommend you to read it. It's not required, but you will learn a lot about the real processor. And this was actually the fastest frequency processor of its time. I guess in 1997. The paper came out a little bit later. Alpha, unfortunately, doesn't exist anymore, as far as I know. It's one of the cleanest ISAs. It was designed by the Digital Equipment Corporation. It's actually its ancestor was the VAX ISA. So it's Digital Equipment went into a total shift and designed a very simple RISC ISA after that huge VAX ISA, right? And Alpha led to there were a bunch of processors. This was not the last one, but this was one of the ones that are at its peak. So it employed a lot of the concepts that we talked about. So I'd recommend that you read that paper. Okay, any questions? No? Yes?
The cache mechanism of doing it that was mentioned by someone. Wouldn't there be some advantages of implementing it that way?
Which way?
Having your cache take care of your translation. So instead of doing it at the processor, you consider the cache level to check whether this memory address maps to this register content maps to the same memory address or not. So wouldn't there be certain advantages of doing it cache?
So you're trying to determine whether this load is dependent on a previous store, right? So you need to communicate all of that information to the cache. So it's essentially where you put this queue structure. Right? You will need to extend your cache to have information about all previous stores that potentially could go there. So that's the downside within the cache. As long as you have this queue, you can put this anywhere, but it's easier to do when you put it closer to your reservation stations, right? Because you don't want to take out, well, you could actually take out your instruction from the reservation station and check this and put it back into your reservation station, but that complicates the design. Yeah, think through the implementation. You will see that it's hard to store this information in the cache because now you need to extend your entries in the cache. Anything else before we move on to DataFlow? Okay, so let's look at DataFlow then. So without order execution, we tolerated latency by figuring out what is parallel and what is not, what can be executed in parallel, right, at an instruction level. And we didn't need any regularity, if you will, in the code. These instructions could be anything. So that's the notion of irregular parallelism. with out-of-order execution, we can exploit, I guess, irregular fine-grained parallelism, if you will, or irregular parallelism. Irregular means that the operations could be anything. Right? We'll contrast this with regular parallelism later on in this lecture. But so this is the code we had last time. Well, out-of-order execution essentially builds a data flow graph for this. Right? So you can, if you look at this machine state, you can get the data flow graph from here. So let's, I guess let me do this. Do I have the code over here? I guess not. So if you look at this code, you can express this code as a data flow graph, right? I guess I'll do that. You have an add, or multiply. Are you guys going to help me? Or R1, R2, R3? And an add, R3, R4, R5. Okay. What is the next one? Another add, R7, R2, R6. So these could be executed independently, right? R2, well, you could even tie them together. R7. Oh, it was R6? Okay. R6, and then R7. What is next? R8, R9, R10. Okay, thanks. Oh, that's also independent, right? R8, R9, R10. And this also that. And then we have a multiply of these. Oh, add of those. Okay. Wait, multiply? Okay. Okay, R7, R10, what is that? R11, okay. And then something of these. Okay, add, okay. Add, and then R5? Okay. So that's how you build the data flow graph, right? And that's what essentially an out-of-order machine does. Right? It takes the first instruction, renames it, and assigns R3 to a tag, if you will. And if you look at the reservation stations here, this is the adder, oh, this is the multiplier. So R3 is really assigned the X tag here. So we really assign X to R3. And then it fetches, what is the next instruction? Add R5, R3, R4. The arcs, if you will, it gets, this node gets connected to the previous node with the tag, which is X. Right. R3, the notion of R3 is gone after a while, after renaming. You really have X here, right? And you get R4. R4 is available. You get the value right away. And you assign another tag here, which is A, to R5 when you rename this instruction. Right? And then the out-of-order machine fetches, what is this? R2, R6, R7. Well, this doesn't look like an R2. R2, R6, R7. And assigns a tag to this value, which is B. Right? And then it fetches this one, R8, R9, R10. And assigns another tag, which is C. And then fetches the multiply, R7, R10, R11. When you rename it, R7 and R10 are gone. Right? You really have the tags associated with this, and R11 becomes Y. So I'm going to remove the register numbers, if you will, because when you're actually executing these in the machine, you don't really have the architectural register numbers. Right? And then the machine fetches this, and then the inputs are A, tags A, Y, and the output is R5, which is assigned another tag, which is D. Okay? So what happens is the out-of-order machine dynamically builds this data flow graph. And the data flow graph is implicitly stored, if you will, in the reservation stations. Make sense? And what does the data flow graph look like? The node is really the operation, and the arcs are the tags that are assigned to the registers via rename. And that's what this figure essentially shows you. Although, for some reason, this instruction got inflated. I don't know why. But that's the essence of out-of-order execution. Building the data flow graph on the fly and communicating these values via the tags assigned to them. So this is really a data flow machine, right? Except it's a restricted data flow machine. It performs data flow-based execution at the microarchitecture level. The programmer didn't specify this. All the programmer specified was a von Neumann or sequential execution code, right? This has nothing to do with data flow. This is all about sequential execution. But we turned it into a data flow graph dynamically in hardware. An implicit one, but it's still a data flow graph. And we kept the ISA based on the von Neumann model. It's still sequential execution that's exposed to the programmer. But underneath, we have data flow-based execution. An operation fires when both of its sources, arcs, have ready values on them. Right? So remember the data flow model at the ISA level? Well, data flow model at the ISA level is putting this graph to the ISA level. And instructions fetched and executed in the data flow order, which means that instructions are specified based on what data values you need. There is no instruction pointer. It's not sequential. Instruction ordering is specified by data flow dependence. Each instruction specifies who should receive the result. That's the ISA level. Right? We did not do that here. But the concept is similar, except we moved the concept to the lower level, microarchitecture level. Right? And that's what makes restricted data flow successful, but the data flow at the ISA level unsuccessful. So people have tried to build machines for a long time at the ISA level. Even before out-of-order, well, I don't want to say before out-of-order execution, because out-of-order execution started with Tomasulo, IBM 36091 in the 1960s. That was before the data flow times, but then because of the lack of precise exceptions, it did not succeed. Because IBM 36091 did not provide precise exceptions. We didn't know the concepts of the reorder buffer at that time. So it did not succeed in general purpose. Then data flow research took off, and researchers looked at data flow model at the ISA level, but there was a bigger problem with precise exceptions there, right? As we discussed. You have all this parallelism in the machine, and you don't have a concept of precise state in your data flow graph, right? Because there's no clean place where you can stop the program and say, oh, I'm always here. How do you draw the boundary, right? There's no sequential view of the machine. But we will still look at this data flow model to give you an idea of what people looked at previously. Okay, so in a data flow machine, a program essentially consists of data flow nodes. A data flow node fires when all of its inputs are ready, when all of its values have when all of its arcs, if you will, are ready. Another way of saying this is when all its inputs have tokens. So I'll use terminology here. You can have tokens in your inputs, and when you get a token, then your input is ready. This is the same as somebody broadcasting your tag, right? Okay. So this could be one representation of the data flow node for multiply in the ISA. You basically take two arguments, and you specify what should the destination instruction be, which is the destination address of the instruction, of the next instruction. So let's take a look at some data flow nodes. Can we actually build a programming model out of these nodes? This is a conditional node. Basically, the way it operates is it has a control input and it has a data input. And control input specifies where should the conditional node pass its output. So if the control input is false, the data input is passed to the destination that's associated with false. If it's true, then it's passed to destination that's associated with true. And the node fires when both of its inputs are ready, right? When you have tokens, if you will, in both of the arcs. And in this case, this is the time when the node fires, and the result is this. It generates a token at the corresponding output specified by the control input. This is a relational node. Well, these are, you can see what you could do with these, right? You could implement branches with this. This is a relational node. Basically, you test the values here. This is how you generate the true and false branch conditions, if you will. So here, basically, this is a comparison, greater than comparison node. If left input is greater than right input, then you generate a true token, if you will. And this, again, fires when both of its inputs are ready. Okay? You could have arbitrarily complex things. Right? In fact, this is one. Do you guys know about barrier synchronization? So barrier synchronization is essentially, this is one way of programming with multiple threads. So you can partition your program into multiple threads, and you can say, these threads need to reach a point, and when they reach that point, they should all serialize. Make sense? Because maybe you need all of the results generated by these threads to do some computation. So usually the way to look at it is you have a serial portion of the program, if you will, and then you launch a bunch of threads. They all operate on different pieces of data, if you will. And at the end, each thread needs to wait for other threads to have completed to continue progressing. Now, why would you do that? Let's say, I don't know, maybe you're counting the total number of words in a book, let's say. And you divided the book such that each page has a thread. A thread is counting the number of words. We could make it even more interesting. The number of different occurrences of different letters in each page. Make sense? So this thread is counting the number of occurrences of each letter, and your goal is to form a histogram of this. A, B, C, D, dot, dot, dot. How many times you've seen A, you've seen B, you've seen C, D, E, F, G in the entire book. This is a very parallel program, so a parallel problem. So you've divided this thread to work on page 1, this thread on page 2, page 3, I don't know, page 10,000. That's a long book. So you have 10,000 threads, and they all, once they're done with their page, you want them to wait for other threads, such that you can add up A's, B's, and C's that they have computed, right? So that you can get the histogram for the entire book. Well, that's the concept of barrier synchronization. You want all of them to stop once they're done. And that's the idea of this node, if you will. Which means that these threads can progress with what they're doing, potentially, or maybe one thread can progress. In this case, all of the threads progress. Only after all of the other threads arrive at that particular point, if you will. And you could have a node that implements something like this. This is a very common parallel programming paradigm. Okay. So you could have other nodes as well. Basically, a small set of data flow operators like this can be used to define a general programming language. You could really implement anything with the data flow. This is the fork that we've looked at. You have primitive ops. You can have a switch. That's the same as what we've looked at. And you could also have a merge operation, which is kind of the opposite of switch, if you will. Merges, in this case, you pass the output. You pass the output the input that's specified by the control input. I didn't explain that very well, but you have two data inputs. One data input associated with true, another data input associated with false, and you pass to your output, to the node's output, the data input that's specified by the control input, if you will. So you pass the true data input if this says true. So it's essentially a predicated instruction, right? If your predicate is true, you take the value that's associated with true. Otherwise, you take the value that's associated with false.
So it's just a mux?
Yeah, it is a mux essentially. Right? It's a mux that's controlled by this. Okay. So we could go on and on, but values in data flow graphs are represented as tokens. Basically, a token specifies the instruction pointer, the destination it should go to, the port of the instruction, should it go to the left part or the right part, and the data. So when you receive a token is sent to basically the destination instruction, which is the address of this. And what did we have? We have the port, left port of this, and the data, which is the result of the add. So when this add executes, what it does is it generates a token that has the destination, which is the address of this multiply, and which port it is going to. This is specified in the ISA, really, because the add specification says one of your destinations is the multiply at, I don't know, some address, and the destination should go to the left port of that, and add appends the result, its result to this. And this token gets communicated to the multiply. And an operator, a data flow node, executes when all of its input tokens are present. And once this executes, well, it receives another token here for its own address, and to the right input this time, and with the result of this plus. When both of its tokens arrive, now this can execute, and when it executes, now it generates another token with the address of this, whatever this is. It's a plus, and it's going to be the right input, and with the result of the multiply. Right? And this is all done dynamically, and we'll see an example of how this happens.
So
Well,
the port is just the tag, basically?
I'm sorry?
So the port is just the tag, basically?
Yeah, port is essentially whether you're going to the left input or the right input. It's not the tag in the register renaming sense, because you need to specify this at the program level, right? So at the hardware level, what the hardware will do is will check whether you actually have the left input and the right input tokens for the address, for the instruction at this address. If that happens, now you match both of the tokens, and this instruction can be fetched and then executed. And you have the results also, which is the left input and the right input. So this is just an example of IP, in this case is 3, port is equal to left, and the data will be X in that case. So there is no separate control flow. Everything is specified in the instruction, and tokens are generated dynamically. Okay. I guess maybe I'll test your data flow knowledge. Maybe we can take a break for 5 minutes, but during the break you can figure out what this data flow program does. I'll give you a hint. N is a positive integer. And I'll give you another hint. I guess there should really be nodes here, but initially this is a 1. Initial inputs are 1 and N. But then when the data flow program executes, this initial inputs are overridden. Basically, when this multiply produces its result, you get that result as input to this branch node. Similarly, when this decrement, if you will, produce its result, you get that as input to the copy node instead of N. But initial values of these inputs are 1 and N. I guess some people don't need the entire break to solve it. I hear some answers. Or you guys don't want to take a break, maybe. And that's a 0, by the way. It looks kind of odd.
What's written on the arrows?
Say it again?
What's written on the arrows?
This arrow, Boolean.
Oh.
So this is the control input that I told you about. Basically, this is a branch node, if you will. If this is true, then it passes its data input to the true output. If this Boolean is false, then it passes its data input to the false output. And that's the output of the entire program, basically. Yes? Okay, looks like one of you got an answer. I don't know if it's the correct answer. Maybe I'll take a vote after everybody has an answer. What is copy? So copy essentially copies whatever it receives to the two different outputs. Remember, you can, in a DataFlow program, you can only specify so many destinations in an instruction, right? Because your instruction length is determined by that. In this case, basically, if you want to send the same data to multiple instructions, we want to copy it.
What is created in 0 do?
What does it do?
Yeah.
Oh, okay. I guess I didn't specify all of these, but basically it checks whether its data input is greater than 0 and generates a true or false value. I know I didn't specify all of these very clearly. So its input is a data value, its output is a true or false Boolean value. I guess I should have said Boolean here. Well, yeah, copy. It should really say Boolean here too. And this is a decrement. Okay, looks like you have some support. Remember, we're also taking the break, so if you already figured it out, you might want to take the break. Oh, this one?
Yeah.
So essentially that's terminated. You don't generate a token and that token dies there. There is no destination, if you will. So if that Boolean evaluates to false, the branch doesn't generate any output, if you will. So that could be a termination condition of this program, for example. You don't want the tokens to be generated all the time. Are you trying to drum up more support for your... Okay, I'll give you 1 more minute and then we can finish the break. Yes?
What does decrement take in?
It takes in...
True or false, right? So what is it decrement?
No, it doesn't take true or false. Yeah, we'll go through it, but it does take the value that's coming here, right? And that value is either passed to true or false output based on the value of that Boolean. So initially, what it takes in is really n, assuming n is greater than 0.
And decrement decrements
By 1, yeah, by 1. Okay. So what do people say? N factorial? How many people say n factorial? Oh, looks like that's the majority. Anybody else? Any other answer? Don't be shy. Okay, so it is n factorial actually. But still, even if you're wrong, you don't need to be shy. But I guess let's run through it very quickly. So the way to look at this is basically you start with some values. And then remember, a node fires when all of its input values are ready. So you start with what nodes have all of their input values ready. Well, obviously, this branch, does it have its input values ready? It has one of the data values ready, but not the Boolean one, right? Because this node didn't fire yet, so we should start with this node, really. It has the input value ready. It starts with n. And that's the only input value. So it copies n to both of its outputs. Now you have tokens in both of the outputs that have n and the destinations. And destinations happen to take only one input. So let's follow this part first, I guess. So n comes here. This node checks if n is greater than 0. It is true, so it generates a true Boolean value. This true Boolean value is copied here and here. Now, let's take a look at, I guess, this part. Now you have n here, ready, and the Boolean true here, ready. This node fires. When this node fires, it's true, and you have n. So n is passed through here. Now this node can fire. It copies n here, and it copies n here. Well, now this node can fire, so n is decremented. At the same time, well, see, that's the interesting part about DataFlow machine. A lot of things are happening concurrently, right? I'm not describing this as things are happening concurrently. So when this copy actually happens, it's copied a true value here, right? And that enabled the firing of this branch at that time. So you had 1 here and true here, which means that 1 goes through here. So 1 was enabled, 1 sent its token here. And after some time, this branch executed and this copy executed, and it sent a token here, and that token was n, right? So what we did was 1 here and n here. We multiply n by 1, and we got n. Is that true? I think so, yeah. So we got n here. And at the same time, we got n minus 1 here, right? So what will happen is, now we have this node ready to fire again. Right? So we have n minus 1 copied here, n minus 1 greater than 0, copied, generates true here. We have n here, n goes down this way because it's true, n minus 1 is greater than 0. And we have, again, n minus 1 passed through here because this is true. And we have n minus 1 here, n here. So the next time we get n times n minus 1 here. And n minus 1 gets decremented to n minus 2. So you could see that this goes on. You get n times n minus 1 here at the input, because that's what the multiplication was. And we have n minus 2 here. Assuming n minus 2 is greater than 0, we keep going. We multiply. What you get here is n factorial until you reach 0. Let's say you reach 0 at some point. Well, at some point 0 is not greater than 0, so you'll get false here. So you will take n factorial at that point, because you must have reached 0, which means that you multiplied n times n minus 1 times n minus 2 dot 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 1. So your output will be n factorial, and this Boolean will terminate what is coming out of this branch. So this branch will not generate a token, because it's not going to be used. Does that make sense? So that's how you get n factorial. And that's how a DataFlow machine actually executes. This is a factorial done iteratively, right? Maybe it's not the best way of exploiting a DataFlow machine, really, because you're really turning this into a loop, iterative loop. Maybe there are better ways of doing this. Yes?
Yeah, this is pretty much a common way of creating factorials in SML also, because it uses value recursion if you have a...
Yeah. So hopefully you now know how a DataFlow machine executes this graph. So if you look at the DataFlow versus control flow, in DataFlow, in a sense, you don't really have a notion of memory, right? let's say these are memory locations. This is your program. A equals x plus y, b equals a times a, c equals 4 minus a. These instructions reference data memory or register locations, if you will. And they communicate through this data memory or registers. Whereas in DataFlow, you communicate directly between the instructions. Instructions are actually linked to each other, if you will. You can study this figure on your own. But that's essentially what we're doing. So what we have is really data-driven execution of some graphical code, instruction-level graphical code. You have nodes as operators. Arcs are data, I/O, if you will, or memory, as opposed to control-driven execution. So only real dependencies constrain processing. Right? Here, you're really constrained by real dependencies. You could have many other things going on in a program, right? Think about it. You could have a huge program that's doing many concurrent things. You're not dependent on the control. There's no sequentialized stream, and operations execute asynchronously. Well, we've already seen that execution is triggered by the presence of data. So people have actually built machines this way. I will briefly cover what those machines do. This is actually similar to out-of-order execution, except this is at the ISA level. So what happens, this is a rudimentary data flow processor, if you will. What happens is when a token, let's start from here. When an instruction executes, it generates a token, which contains the data, its result, the destination of the result, which is the address of the instruction, as well as the left or right input, and something called a tag. And tag this is actually to identify the context of the instruction. So you want to really have multiple copies of the same instruction, right? Why? Because you have a loop like this. Remember, you want to ensure that different copies of the instruction receive the correct corresponding tokens at each of their inputs. Let's say you want loop iteration 1, let's say. In the first loop iteration, you want both of your inputs. Well, I guess in this case, we have this instruction that have the inputs here. You want both of the tokens to be from the same iteration, right? You don't want tokens from different iterations to fire this node, if you will. Similarly, if you want to do a function call, for example, you could have this thing called by many different places. You want to distinguish between them based on a context ID. And that's the tag here, if you will. So an instruction generates a token based on the context ID. This could be the iteration count. It could be the calling context, if you will. And it's sent to this matching area. So the goal of this matching area is to store the tokens that are currently not matched. So if an instruction requires 2 tokens, you want both of them to be ready to fetch that instruction, right? And you store the tag and the destination here and check if there's a matching token for the same tag and the same destination. And if there is a matching token, then you group them together. Now you have data 1 and data 2 for a 2-input operand, for a 2-input operation. And you generate the tag, and you have the destination instruction pointer, if you will. And you have an instruction fetch area to fetch the instruction. You go to memory, using the instruction pointer, fetch the instruction, and now generate an execution package, if you will, which has the operation, which contains its destination, of course. In the ISA, we specified that. And you package the data values, and you have a tag that's passed down. And the instruction executes. It generates the result using data 1 and data 2 and the opcode, and it passes the tag and destination. So this is a data flow machine. It keeps operating like this. And you could fetch 1 instruction. You could fetch many instructions at a given time. So this pool of unmatched tokens, if you will, are those tokens that wait their corresponding tokens to fire the associated node. So I guess I will skip this, but this is the high level. This is at a high level how the data flow machine works. In a sense, draw the corresponding analogy to an out-of-order machine. An out-of-order machine essentially fetches the instruction first and ties the instructions together, and there's still a matching area, right? That's the reservation stations, if you will. Right? You match different, you match the tags of instructions, tag of the values that are produced to the source tags. And if both of your source values are available, then you can fire the instruction, if you will. You don't need to fetch it because you've already fetched it, right? Because control flow comes before the data flow, if you will. Okay. Is this clear? Yes?
With this kind of a control, aren't we getting something like a kind of clockless computing environment where we just depending on data to come in and that's when things fire off?
It's asynchronous, yes. It's asynchronous, so there's no control flow, if you will. But you can still implement. The clock is an underlying implementation concept, right? You could still implement this with a clock. Okay? But it's asynchronous. I think that's the word you're looking for. Okay, so if you look at this is one example. This is the graph we're looking at conceptually. This is the encoding of the graph in memory. So this is what a data flow program is, if you will. You have op1 specifying its destination. You have at location 109. You have op2 specifying its destination. And the destination is always what is the address of the instruction and what is the port, left port or right port. So if you look at op2, let's take a look at op2. It's at address 113 and its destination is 120R. Well, what is 120R? It's this add's right port. You have an add here, and its destinations are 141, op3, and 159 left. In this case, you don't have a left or right because it's a unary operator. Okay? So if you look at the execution of this particular instruction, what happens is, let's say it gets the right value and it will become ready. Let's say this is you have snapshot of the execution. There's a waiting token. The left value is waiting, and you have the tag, and this is the data value for that left operand, if you will. And somebody produced the right operand. Well, you can figure out what that somebody is. That somebody is op2, right? And it generates a token with 120R, tag, and the result. This wait match unit looks up some associative memory and figures out that, oh, there's some other token that's destined for 120. And now it can create an execution packet, if you will. Well, actually fetch packet in this case, saying that fetch 120, and these are the tags and these are data values. That the instruction gets fetched from program memory. Well, what is fetching the instruction? Basically, you get the opcode, you get the destination, and you also pass the tag and the results. And the instruction gets executed. Basically, now you add the two values based on the opcode, and you generate. And then after its execution, you form tokens. In this case, you form two tokens because you have two destinations, right? What are the tokens? One token goes to 141 with the result of the add, and one other token goes to 159 left because the result of the add goes to two different places, right? Okay? So that's how data flow works. And I will not talk about this, but you could think of the same thing. Memory operations flow through a similar thing. So a memory operation is essentially this. You fetch from address and generate a value. Right? And this memory operation becomes available when this input is available, the address is available, and the memory operation executes. An execution of the memory operation is, well, it shouldn't go through the ALU, of course, so it generates a fetch packet to memory, and that fetch packet goes to memory. When the memory responds, you generate a token with the data value from memory, well, values V in this case, the values V, and the destination instruction, which happens to be at 207, and it goes through the token queue and wakes up, if you will, the destination instruction. So you could design a full system using these principles, and that's what people have done with the. Actually, there have been many data flow machines. Manchester data flow machine is one I would recommend to you to take a look at, and the machine operates essentially the same way. You match, figure out which instructions should be fetched. You fetch the instruction, you execute the instruction and generate the tokens, and tokens go to the matching store. And if you have big programs, the problem is this matching store overflows. So in a sense, this is a very good way of exploiting irregular parallelism. The problem is, when you have a huge program, aside from the problem with precise exceptions, when you have a huge program, you cannot control the parallelism. And this has been a problem with many data flow machines. They have these overflow units that store huge number of tokens, if you will. And the hardware becomes complex, and it becomes difficult to manage the parallelism. Because, again, you're not restricting your window to anything, right? In an out-of-order machine, your window is restricted because you're fetching instructions in control flow order. Here, you're really at the mercy of your data flow graph, if you will. If your data flow execution enables some instruction that's a totally different portion in your data flow graph, which could be huge, then you've got to fetch those instructions. And they will generate tokens, and they will cause your matching store to overflow. That's why you have these overflow units. And this has been a real problem in data flow processors in the past. Okay, advantages? Well, very good at exploiting irregular parallelism. You could give a data flow graph, and you could actually find parallelism everywhere in that data flow graph using this kind of machine, because only real dependencies constrain the processing. There is no control flow dependencies anywhere. Disadvantages? Many, actually. We already described there's no precise state. As a result, debugging and interrupt exception handling is very difficult, because you could be anywhere in your huge data flow graph. Right? How do you, even if debugging was not difficult, let's say, how do you actually save that state? So, right, it's a lot of state. Bookkeeping overhead, I already told you, tag matching, too much parallelism, and I already described that. And I will not go into this, but think about what if you had mutable memory? How do you implement that? Like, how do you have linked lists in this sort of machine? How do you have pointer-based data structures? Because we didn't talk about the concept of memory very well, but it turns out it's difficult to do. So, as a summary, I already told you all of these. Data flow at the ISA level has not been successful, really, because of these problems. But data flow implementations under the hood, if you will, not exposed to the programmer, have been extremely successful. That's what we call out-of-order execution. That's what is restricted data flow. Because the programmer can reason about what's going on in the machine. They can debug their program. They can handle interrupts and exceptions. You have this clean interface to the programmer through which the programmer can reason. But underneath, the hardware extracts similar kinds of parallelism. It's probably a little bit more restricted. But for the given amount of hardware, it's not clear whether the hardware actually extracts less parallelism than what you could do at the data flow ISA level. That could be some food for thought for you. Okay, so if you're interested in this, here's some further reading. It's a good paper. It requires some thinking, but you can see some real data flow graph examples, as well as data flow ISA, data flow programs in that. There have been many machines implemented in the 1980s, and until early 1990s even, at many different institutions around the world. Manchester was one of the pioneers in this. But they died down once Pentium Pro came out, and they actually applied restricted data flow principles to a sequential ISA. So, in a sense, I'm describing this to you because I think I view this as the essence of computer architecture, if you will, because where do you make that trade-off? What do you expose to the programmer? We're going back to that again, right? Out-of-order execution made that trade-off very well. It did not break this nice, clean-cut, precise exception model, if you will. Whereas data flow was a very, very interesting experiment, and it did actually result in a lot of research, but it was very hard to actually carry to practice in real life, because real life is really based on that software stack that you need to implement on top of it. And if the programmer is not able to reason about that, it's very difficult to do so. Okay, we still have time. Any questions on DataFlow? It's a very exciting concept. But hopefully you know how to read DataFlow graphs and make DataFlow graphs now. So let's take a look at a very different kind of parallelism. Looks like we're not going to be able to finish vector processing today. DataFlow was very good at exploiting irregular parallelism. Let's take a look at kind of an opposite end, if you will, exploiting regular parallelism. Let me skip this for now, but we will get back to that. What is data parallelism? In data parallelism, concurrency arises from applying the same operation on different pieces of data. We call this a single instruction, multiple data. So a single instruction, single operation is applied to many different data elements. For example, think about the dot product of two vectors. You have two vectors, each a billion elements, and you want to, let's ignore the dot product. Let's say you want to add the two vectors. What you do is you apply the add operation to each element of both of the vectors. Right? So there's a very simple way of specifying that operation. You just tell the machine you want to do an add. You tell the machine how long your vectors are, and you tell the machine the beginning addresses of the two vectors. That's it. Right? You can represent that operation very compactly. And you can get a massive parallelism out of this, a billion operations specified with a single instruction. Okay. So that's the idea of a single instruction multiple data engine, if you will. You can contrast this with thread parallelism. Concurrency there arises from executing different threads of control. If you've done multi-threaded programming, it's different. Contrast this to DataFlow. Concurrency here arises from executing different operations in parallel, right, in a data-driven manner. Here we have the same operation applied to many data elements. Well, this is another way of exploiting instruction-level parallelism. You have essentially a single instruction doing many operations. Operations happen to be the same. Okay, this is called SIMD, as I said. And there are two varieties, if you will, which are essentially the same. They're duals of each other. Basically, single instruction operates on multiple data elements, and you have multiple processing elements. If you're an array processor, an instruction operates on multiple data elements at the same time. If you have a vector processor, this is the traditional definition of a vector processor, an instruction operates on multiple data elements in consecutive time steps. So let's take the example of adding two vectors. In an array processor, let's say these are your vectors. Vector 1, vector 2, element 0. Well, I guess I should do this. 0, 1, 2, 3, 4, dot, dot, dot. In an array processor, you could do all of these additions in parallel because you have enough adders to do this. In a vector processor, you can have a single adder, and in one cycle, in the first cycle, you add the first two elements. You add the first element of each vector. In the next cycle, you add the next element. In the next cycle, you add the next element. In the next cycle, you add the next element. You still specify the big chunk of operations with a single instruction. So these are duals in terms of time and space. And we will take a look at that, actually. Oh, actually, I don't have it here. But basically, that's the difference between array and vector processors. An array processor, you can do the operations in parallel at the same time. Because you have multiple adders, if you will. In a vector processor, you can do different operations. You can do the same operation in consecutive time steps on different elements. Okay, so we've seen VLIW, right? Do you remember VLIW? Very long instruction word. We've discussed this in different lectures. We didn't go into detail as to how to implement it. But in VLIW engine, what the compiler did was it packed instructions like this in a single instruction. You have a single program counter pointing to multiple operations. and the compiler guarantees that they can be executed in parallel. And you have multiple processing elements that basically you access memory, you get these operations that can be executed in parallel, and you execute them because the compiler guarantees that they're independent. If you want to contrast array processing, if you will, with VLIW, this is what an array processor does. Again, you have a single program counter specifying a vector operation. And let's say your vector length is 4 in this case. This essentially specifies 4 different operations that can happen concurrently. The first processing element, well, in this case, we're incrementing a vector register by 1, if you will. The first processing element takes the first element of the vector, increments it by 1. The second processor operates on the second element. The third processing element operates on the third element. The fourth one operates on the fourth element. Make sense? So you've actually specified with a single instruction 4 operations. VLIW is similar. Again, you have a single instruction, but 4 operations are already specified in the instruction, and they can be different. In a sense, this is more flexible. Right? Whereas this is less flexible. Yes?
What was VLIW different than superscalar?
Okay, so VLIW compiler guarantees that these instructions are independent. Superscalar, there's no guarantee. You fetch 4 instructions, and they could be dependent or independent. And these all have the same program counter also, whereas in superscalar, you have different program counters for different instructions. Yes?
Which leads to better performance.
Which leads to what?
Better performance, superscalar or VLIW? Because it seems like VLIW.
Okay, we can have that discussion later. That really depends on how well you can pack.
Right.
There are a lot of issues. We will get back to VLIW later on. Yes?
So you won't need any dependency logic.
Exactly, yes. In this case, because the compiler specified these are independent, you don't need any dependency check logic for these instructions in parallel. So that simplifies the hardware. But we will get back to VLIW after we cover vectors. Yes?
So where does most of the performance improvement come from?
In vector processing?
In VLIW?
Compared to what? Compared to?
Just like single instruction, single table.
Okay, so because you can now fetch multiple instructions at the same time, right? Multiple operations. It's essentially multiple instruction fetch, decode, execute. You can improve your IPC, instructions per cycle performance.
So in this
Okay.
example, like it's actually not that fast because the loads take much longer than the other.
It depends. If you're hitting the cache, you may have the same latency, right? Okay. 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 So let's go over vector processors a little bit, and then we'll continue in the next lecture. So a vector, you hopefully know, it's a one-dimensional array of numbers, and many scientific, even commercial programs use vectors. So let's say we have this program. A vector processor is one whose instructions operate on vectors rather than scalar values. So far, we've looked at scalar. MIPS is a scalar ISA, for example, right? You operate on single data element at the same time. We're going to design an ISA that actually operates on vectors. So what are the basic requirements for this? We need to be able to load and store vectors, right, into registers. So we have the notion of vector registers. A register doesn't contain a single value, single scalar value, but now your register is essentially a vector. So in a scalar ISA, your register contains one n-bit value, right? Where n is the width of your register. In a vector processor, we're going to make this, I guess, m n-bit values. Which means that you can store an m element vector. This is the 0th element, 1, 2nd, 3rd, and then m minus 1th element. Okay? And you need to be able to load and store these vectors into those registers. You need to operate on vectors of different lengths. Right? Sometimes you want to operate on, your vectors are small, 4. Sometimes it's 16, sometimes it's 64. Right? You need to be able to have that programmable. So we have the vector length register that's programmed by the programmer to do this. And elements of a vector might be stored apart from each other in memory. Right? This is the idea of a stride, distance between two elements of a vector. If you look at memory, your vector could be laid out such that consecutive elements are in consecutive locations, but this need not be the case. Think about a matrix, right? In a matrix, you have rows and columns. And let's say this matrix is laid out in row measure order, which means consecutive elements in a row are in consecutive locations in memory. Which means that this is at location, let's say your base is at A. This is at location A. This is at location A plus 1, A plus 2, A plus 3, A plus 4. Let's say A plus 63. And the next row starts at A plus 64, 65. Dot, dot, dot. And let's say, I don't know, you go somewhere, X here. If you want to access a column of this array, they're not in consecutive locations, right? They're 64 locations apart from each other. And sometimes you may want to access a column of this array. You don't always access just the row. Which means that you want to make that programmable also. You want to load this column into your vector register. And how do you do that? Well, you specify a stride. Stride is the distance between two elements of a vector. And if you want to load this column, you say, my stride is 64. And my vector starts at address A. And you have a vector load from address A into a vector register X. And you set, I guess, the vector stride register to 64 to begin with. And this vector load, essentially what it does is it starts from A and starts loading the vector register with address A plus 0, the data in address A plus 0. First element goes there, A plus 0. The second element at address A plus 64 goes here to the next element. The next element at address at A plus 128 goes here to the second element of the vector register. So that's how you can actually get this entire column into a single vector register by specifying a stride and a vector length also. In this case, vector length is dependent on what your hardware can support as well as what is the maximum you have here. Okay, so I think I will stop here and we'll continue vector processing on Wednesday.